Welcome to our Solutions for NanoAnalysis podcast, brought to you by Bruker NanoAnalytics. We look forward to bringing you a new podcast regularly. My name is Cody Morton. I'm a marketing communications specialist at Bruker NanoAnalytics and an information enthusiast. If you like to learn from specialists in their field and hear what technologies are solving their problems, you will enjoy this podcast. Every session, we will focus on a different problem that our colleagues face in the lab and in the field. Some of the solutions will be a variation of ideas you may have heard before or even worked with. We will bring you these topics in a new and interesting way and introduce you to updated and thought-provoking results. We will talk about how the problem was dealt with in the past and what we're doing to solve the problem now and perhaps even envision future solutions. Join us as we talk solutions with a variety of scientists and technicians in many different industries in the Solutions for NanoAnalysis podcast. Welcome and good morning. Dr. Ronald O'Malley is joining us from the Materials Science and Engineering Missouri S&T is what is in your signature line.
Yep.
Tell us more about what you do there in Missouri.
Okay. Well, thank you and good morning, Cody. I'm a professor here at Missouri University of Science and Technology that works in steel-related research, and I actually hold the Iverson Chair Professorship for Steelmaking Technology here at Missouri S&T, or Missouri University of Science and Technology. But I also run a steel research center that we call the Peaslee Steel Manufacturing Research Center. I've been here about 8 years now, and that center has grown significantly and works in a wide range of steel-related research areas and is fully industry funded. So it's a consortium of steel producers and suppliers. One of the big areas that we work on in this area is steel quality and the improvement of steel performance. And to that end, a lot of the work we do is focused on how do we engineer steels and their processing to improve those properties. And this includes work that goes all the way back to the primary steel production process, either the blast furnace BOF-based route or the electric furnace steelmaking route. In fact, more recently, we have worked more closely on the electric furnace steelmaking route for steel production, which is a more energy efficient route. It's approximately 70% of the steel produced in the US today is actually made by the electric furnace route. And that route actually has some interesting challenges in producing high quality steels that actually ultimately have been challenges to the industry that they have been consistently overcoming and moving up the quality food chain to produce the very highest quality products that the steel industry produces.
And then, Ron, before we got started, I really wanted to ask you, what made you interested in science as a kid?
That's a really interesting question. As a kid, very young, I had family that was always giving me science-related stuff, and I had science kits. And I had exposure to, a shop to build things as part of, what my dad's hands-on experience were. So that's probably early on what got me interested. As I went on later in life and went to college, I was lucky enough to get involved in the field of metallurgy. And that was through, a university that had some really outstanding professors that had real-world hands-on experience. And they introduced me to the field. I got, molten metal in my blood, so to speak. And really, my career has been in that field ever since. Now, I'm a little bit unusual as a professor because I'd spent 30 years in industry before I became a professor. And so I brought my experiences in the industry back to the university here and have tried to play that role that those professors that got me excited about the field did back in my early days. So it's an exciting program. I'm lucky enough to have found this opportunity to join Missouri S&T and this Steel Center. And actually, when I talked to my wife about making this move, which was a big move for me, moving out of industry back to academia, I described it as my dream job. And for 8 years now, it has been that. So I love what I do, and I love working with students. And the industry is my family. I've worked with most of the industry technical groups throughout my career through AIST. I just finished a stint as AIST president just a month ago. So it's like working with your family, and and most of them aren't even dysfunctional. They're actually.
So, Ron, what is the problem that we're talking about today? Because I know that we're going to be talking about a lot of these things that you've been studying.
Absolutely.
More than just the past couple of months, years, etc. Yes. So tell us about what the problem is that we're talking about today.
Okay. So in steel quality, one of the key areas that we are concerned about is how steel performs in service. And the generation of oxide in the steel is a natural part of the steelmaking process. And our concern is really with how steel performs in the presence of what we call inclusions, which are typically oxide defects. They can be other types as well. How it affects the fatigue performance, how it affects formability and defect generation. And in the end, our goal is to try to produce what we call very high cleanliness steels with very low residual oxide contents, and with oxide types that are benign to the performance objectives of the steel. So I don't know if that makes sense to you or not, but in certain types of steels, if we have oxide inclusions in them, but they're readily deformable during the forming process, they're benign to the product. But if they're hard and they can break during the forming process, they can tear open the surface and create a defect. So the real question is, how do you engineer these inclusions to actually be the proper type with the least quantity and still, maintain the objectives of steel manufacturing? I'll take a step back and say, when we manufacture steel today by the electric furnace route, we use a lot of oxygen, and oxygen is used as essentially a chemical energy source in addition to the electrical energy source to actually help melt the steel. But oxygen is also used to remove carbon down to the low levels that are required to make high formability steels, typically below 0.05 carbon, down even to ultra low carbon contents, which might be as low as 30 to 50 ppm. And the oxygen used in that process actually dissolves in the steel. And if you were to take that steel and just try to solidify it as is, you would actually generate gas blowholes, bubbles in the steel during the solidification process. So a necessary step in steel manufacturing is the deoxidation of those steels. And that's done through the addition of deoxidants, typically in the form of silicon, manganese, and aluminum. For a lot of the high quality steels, aluminum deoxidation, or sometimes called aluminum killing, is the dominant process that is used for deoxidation. Now, the downside of deoxidation is that when you add aluminum to high oxygen steel, you form a solid oxide product. And that product is an inclusion. It's dirt in the steel, if you will. And how we deal with that dirt, how we remove it, is actually very critical to the downstream objectives I just talked about.
Let me ask this real quick. Ron, how long has the electric furnace route been used? The history of steelmaking, there's been things have gotten better and better and better. I assume the electric furnace helps with the inclusions.
Well, yeah, the electric furnace is actually a method by which you can use large quantities of recycled scrap.
Oh, okay.
So it actually is a more efficient process because you can reuse steel as opposed to producing primary steel. Now, in that process, the electric melting is often supplemented with chemical energy by blowing oxygen with things like supersonic oxygen lances and carbon injection. But in that process, the steel that is produced has to be refined downstream from the EAF. And that's part of what leads to complications in this inclusion evolution process. EAF's been around a long time, but the advent of the mini mill technology, the production of thin slab casting, direct rolling technologies has really advanced the state of electric furnace steelmaking here in the US from possibly about 20 to 30%, up to now 70% of the steel today being produced, and almost all the new steel mills being produced in the U.S. being produced or being built are electric furnace based. Probably the latest one is Big River Steel, which is now part of U.S. Steel. So with all that, we use deoxidants to tie up the oxygen and generate these oxides. And one of the things that we need to understand is, what do these oxides look like? What are their shape, their size, distribution, their composition? How do they evolve over time in the steelmaking process? And this is where the technology that we're talking about today actually comes into play, because we can sample these steels at various stages in the process, take solid sample pucks from the steel, liquid steel at different stages, grind them and polish them, and then look at them under the SEM and actually characterize those inclusions. And in doing so, we can actually study the evolution of the inclusion morphology over time and understand how subtle changes in steel processing affects these steel inclusions, their size, their shape, how easily they agglomerate, float out of the system, and so forth. And ultimately, their final form in the final product as we go to the continuous casting process. So let me take a step back then and basically describe a little bit of what we're doing. One of the things we've done with the technology that we're talking about here is that we've gone into steel plants and we've done what I would call forensic sampling of the steelmaking process in a variety of different plants. As part of the consortium, we have access to a large number of plants, and we've had students sample through the operations of steel plants here in the US and even abroad to look at how individual plant practices influence the evolution of this inclusion morphology. And we've found a number of really surprising things in the process that are ultimately helping us define the best paths for producing low oxygen steels with the right inclusion morphology.
Now, you talk about doing a forensic sampling, which I assume means going back after things have been processed along the way and just...
Yeah, or sampling intermediately along the way, but looking at a practice that's in place and then forensically analyzing it for the implications of that process sampling. Yeah.
Are you then able to ultimately take that information and recommend changes to make and tweaks to the process to clean up what you're seeing?
Absolutely. Absolutely. And of course, the first stage you can do here is you can compare different plant practices. But the other thing we can do, and we do here at Missouri S&T, is we have our own steel foundry here, and we can produce 200-pound steel heats and actually do experiments in those heats here at the school and actually evaluate different alternative practice routes and also do specialized sampling that's hard to do in the plant environment. For example, we've developed specialized samplers that we can take steel that is essentially representative of the steel tapped out of the electric furnace with very high oxygen contents, and then we can do deoxidation here in the lab of those simulated melts under environments that allow us to do sampling and capture of the inclusion evolution development from 1 second after deoxidation up to 20 minutes after deoxidation. So we can sample at resolutions that are really difficult to do in the plant world, but do them here in the lab. And that's actually told us a lot about what controls the evolution of inclusions and the inclusion morphology. So where IntelliSEM comes in here is what it allows us to do is do statistical analysis of these inclusions. Any given sample will have many, many thousands of inclusions in it. And we're interested in the shape of all that overall inclusion population, its chemistry, the size and aspect ratio, and really even down the road, the heterogeneity of the inclusions as well, and how inclusions coagulate with one another and form complex inclusion types. In some of the work we've done here in the lab, we have observed that the initial generation of inclusions out of the electric furnace, which is often an emulsion inclusion generated by supersonic oxygen injection, actually dictates the size of some of the downstream inclusion populations that you develop after killing the steel. And this is actually an interesting finding because most people don't talk about this. Many of the theoretical analyses assume that those inclusions form by homogeneous nucleation. And we've been able to show, in fact, that the size populations match those of the emulsion inclusion population due to heterogeneous nucleation after the initial stages of deoxidation. That understanding also helps us understand the evolution of the inclusion morphology, because these emulsion inclusions will be converted by the killing process, but won't completely consume the oxygen in the oxide form. And then they form very complex shapes after that by growing branch structures off of this heterogeneous nucleation site. And all of this, I'm sure, sounds very technical, but what it really says is that the shape and morphology of the inclusion is very much dictated by that early stage practice in the EAF, which is something a lot of people have not talked a lot about in the steelmaking process.
Why do you think that is?
Well, I think the sampling and the analysis has been exceptionally difficult. And with the advent of IntelliSEM, we've been able to accurately measure these size distributions, which is something that it really was not able to be done before, right? You know, being able to analyze a large sampling of an inclusion population actually tells us a lot. The shape of that inclusion population tells us a lot as well. And I'll give you some examples here in a few minutes, but the shape of the inclusion population evolves over time during the steelmaking process. And it will migrate from a log normal type distribution to a fractal or a log linear type distribution with aging over time. And this is because inclusions interact, stick together, coagulate, and larger inclusions float and are removed from the system. So the evolution of the shape goes from a curved population density function to one that is flattened over time as you go through the cleaning operation and float and agglomerate out these inclusions. But what's really neat is that we can see cases where a good job hasn't been done protecting the steel after all that work is done, and reoxidation has been allowed to occur. And if oxygen is re-injected back into the system, you generate a whole family of new inclusions from that oxygen ingestment into the system. And it actually reverts the inclusion population density function back to a curve distribution. And we've been able to use this because of the IntelliSEM's statistical capabilities to relate the shape of the inclusion to identifying sites where contamination has taken place and oxygen is leaking into the system.
Where do you think this technology and this analysis is going to go in the future? Things will get much cleaner, things will stay much cleaner in the future?
First of all, these size distribution tools used in the plant environment will allow people to better essentially target where their steelmaking processes might have gone awry. I'll cite an example in a sampling study we did in a Korean plant. We found that the steel in the tundish was actually not fully protected with the tundish flux practices that were being used, and oxygen was actually able to get into the system and generate new inclusions. And in generating new inclusions late in the process is exceptionally bad for the casting process because it causes clogging of the refractory components and ultimately can result in shutdown of the caster due to lack of supply of steel, because these oxides will actually build up and clog essentially the delivery systems, the shrouding systems that are used to try to protect the steel. And so if we can identify those points, we can fix the problems. And that's certainly one great benefit. The longer range benefit is that we can look at these distributions and identify conditions where the inclusions actually will agglomerate, coarsen, and float more quickly so that we can get lower total oxygen contents. And another example here is that we've used these population distribution functions to identify what happens just during argon's bubbling or stirring, which is used to promote inclusion, agglomeration, and removal. And if we look at one population that is a solid distribution of oxides, predominantly pure alumina or any other solid inclusion, and we compare it to an inclusion that has been modified, say, by calcium treatment, where it's converted into a liquid inclusion, we find that the solid inclusions interact strongly and remove much more efficiently than the liquid inclusions. And so what this says is there is a preferred path by which you do rinse stirs in the steelmaking process to remove oxides.
Was that a surprising finding?
It was originally, yeah. I think there was a lot of debate in the industry about what is the best practice. For example, do you focus your time on rinse stirs in the LMF after calcium treatment or before calcium treatment? And it turns out this type of work is showing that dedicating your rinse time before the calcium treatment event is much more effective at reducing total oxygen levels. So, this is just using size distribution, in the IntelliSEM environment. You also have these tools that you can essentially examine the inclusions, examine how they're converting with time, and, how they're developing into complex morphologies, basically co-inclusion, precipitation, and other phenomena that are also very important to the steelmaking process. And so we can look at chemistry, we can look at shape and size distribution, all in combination in a large population of inclusions with this tool.
That's really amazing, all of this information that you're able to get. With the IntelliSEM and what your students are doing there, what is one thing that you're sure that the students understand and take with them when they go into the industry, when they go into their job?
That's a really good question. Our students often end up in the steel industry. One student in particular who did a lot of this isolated inclusion work here in the labs is now working at Nucor. And he is applying this technology directly in the plant environment and using these tools to further enhance beyond the work we've done here in the university. So, the directly applied in the real world, it's certainly what we like to do here at Missouri S&T. And this tool has been, so invaluable to us to actually develop these whole programs that the industry is interested in. And we have a really strong collaboration with many industry members on.
Mm-hmm. Now, Ron, earlier I had asked, what would you recommend a listener do for more information? And you had mentioned a study paper that had been worked on. Can you tell us a little bit more about that?
Yeah, we have a series of papers we published. There's a couple of MET-Trans B papers that have been published on a lot of this work on heterogeneous nucleation and inclusions, and the role of early emulsion inclusions in the formation of inclusion morphology. I've also published, a paper with AIST as part of the Peaslee Clean Steel Symposium, and there is actually a memorial volume that's been published in that symposium as part of that, where I actually have a general description of the technology of inclusion evolution in steelmaking. So,
that's great.
Those are great resources. Yeah.
Yeah, we'll make those available in our show notes. So is there anything that you know now that you would have told Ron working in the industry, watch out for, or you could do this better?
Well, it's an interesting question. I mean, the people in the industry now have way better tools than I had when I was going through this in my early years. If I did a statistical study on inclusions many years ago, it would have been 8 inclusion analysis in a sample and call that characteristic. Now it's tens of thousands, right? You couldn't do that by hand. The automation capabilities today make that taking full advantage of that, learn the new tools. But I would also say, get involved with anything new going on. Probably some of the best times of my career were stepping out and working on new programs that were cutting edge and commissioning of new equipment, because that's where you get to try all the new stuff. Mm-hmm. That's what I would say is the most exciting thing working in the industry.
That's excellent. Is there anything else, Ron? I feel like I have opened a large encyclopedia and I'm on page 1. I'm just like, what is the big takeaway? What else can I learn?
Well, I'd say going forward, we're not done by any chance. I mean, these new tools are great, but I look at what's coming. A lot of the work that we've done on inclusions, we've had to go to inclusion extraction to look at them in 3D. We're getting ready to do micro CT analysis to be able to look real time, really at these 3D inclusions. The IntelliSEM systems, we have often talked about what's the next generation there. And one of the things that we would like to see happen there is that this equipment get fast enough and the prep times get fast enough that you could use them in real time in the steelmaking operation. So today we look at them, I mentioned forensically, we look after the fact. But if we could do these things in real time, boy, what a boon that would be. A steelmaker be able to characterize an inclusion distribution and absolutely tailor the calcium treatment practices, the desulfurization strategies to the information that he has in hand. That would be wonderful. And, we're doing a lot in that area, and there's so much else. There's all new sensor solid technologies being developed. One of the areas we're working on now is developing sensor technologies for extreme environments for the steel industry. We're using fiber optics a lot right now and being able to apply those to get highly distributed temperature measurements and temperature measurements at steelmaking temperatures using sapphire fibers, for example. And this is just opening the window of opportunity to be able to see the process as it happens. And IntelliSEM is one of those tools, but combining IntelliSEM with other technologies like cathodoluminescence, we've talked about as future technologies, or other multiple applications, maybe using Raman or some other methods. Where all of these technologies give us a whole host of new pieces of information to better understand our process.
Oh, thank you so much, Ron. I really appreciate your time. Now, I wonder if I can put Mike on the stand. And Mike, did he represent IntelliSEM completely enough to garner the right information, or is there other things that you would love for people to know?
No, I think he did a great job of outlining, where the idea of the automated microscopy started and what's driving it forward. You're talking about next steps. I mean, we first started this working with the Department of Energy, this project back in the late 1990s, early 2000s. There was a lot of skepticism from the industry because at that time there was a lot of work. It was mostly done optically, and a lot of the microscopy with electron microscopy was done manually. And so all the forensic analysis would be looking at the larger particles, things greater than 5 or 10 microns, sort of the massive macro inclusions you would see. And through the work that we had done with industry partners like US Steel, we were able to shift some of the thought process away from, obviously, we're looking at a small puck that represents a 25-ton heat or something like that. The statistical likelihood of us seeing that macro inclusion that may end up appear downstream is very low. It's the needle in the haystack. And so we were able to start to show that by understanding the building blocks of based on the size of the inclusions and the chemistry of the inclusions, we could, with some level of confidence, predict whether or not you could potentially have problems downstream in your final product samples. And so over time, it shifted from looking at the large macro inclusions down to, right now we go down to typically around 1 micron is sort of become sort of the industry standard. A lot of that is based off of the SEM technology using standard tungsten source electron microscopy. The minimum size you can really get with some decent resolution is probably down to 1 micron. Doing it in such analytical conditions that analysis is done within an hour or two as opposed to days. Though now as the electron microscopy is getting better with field emission microscopes and things like that, we're starting to push those boundaries. You're dealing with ultra clean steels. So now, the steels are now stronger and thinner. So the size limits of what are considered, possible inclusions that could cause some deleterious effects have now changed, and they're getting smaller as well because the steels are getting thinner. And so we're starting to look at things in the submicron down into the nano inclusions. And I think some of these tools now available as they get better will, potentially open up a whole new world of understandings of inclusion formation and characterization.
I will echo a sentiment. The field emission technology is certainly pushing our ability to analyze into the smaller and smaller sizes making that possible. Where previously a lot of that you had to rely even on TEM methods. Things like field emission are starting to bridge that gap between the 1 micron and the nanometer scale to give us a lot more meaningful information in the very early stages of inclusion population growth. So it's actually a really great tool. We've actually worked with Mike on looking at some of those things for new classes of steel, such as high efficiency motor lamination steel, where the inclusion distributions influence the magnetic permeability and core loss of steels used in motors for new electric vehicles, for example.
Well, here I thought that Mike wouldn't have anything to add, and he did. He wowed us. Thanks, Mike.
Yes.
Appreciate the extra information. I think one of the amazing things is to think how the industry has evolved and how the technology of analyzing has to keep up with the evolution of the industry as well. It'll be interesting to see where things go from here.
I can tell you there's lots of exciting stuff on the horizon. The new world of hydrogen steel making is coming upon us now. Low emission steel production, electric furnaces with intelligence, embedded fiber optic systems and real-time feedback for dynamic control to respond to changing scrap material inputs, new steels, as Mike mentioned, that are being used for lightweighting vehicles. There's a wonderful world yet ahead of us, and lots of work to do.
Thank you to our speakers today. During today's discussion, we talked about the IntelliSEM technology that used Bruker QUANTAX EDS on the SEM. Find more information in our show notes about the EDS technology, as well as other information mentioned today. If you would like more information about today's topic or to submit a topic idea, please email info.bna@bruker.com. You can also check out more information in today's show notes. Join us next time as we look at a new solution with more scientists and technicians in all sorts of industries.